Hi, good morning and welcome to another edition of Data Center Insights by Intel. I'm Corey Claddock, and this morning we're taking a deep dive into Intel Network Builder's technology from Amartus. This morning we have Olga Havel, who is the head of product strategy at Amartus, providing thought leadership on products and solutions for management and orchestration of next-generation services and networks. We also have Maurizio Sterlezzi, who is Amartus CTO since 2004 and has responsibility for the technical direction of the company's solutions. This morning, they'll be taking a look at dynamic programmable service orchestration, which is the key to exploiting NFV, SDN, and cloud technology. All right, Olga, why don't you go ahead and get us started?
Thank you, Corey. I first want to thank you all for attending us. I also want to thank our partner Intel for this opportunity. In the next few slides, I will introduce the need for the real-time multi-vendor OSS that must provide dynamic programmable service management and orchestration solution for NFV, SDN, cloud, and wide area network. I will start by describing the current problems that service providers are facing and will present the required solution. I will also introduce the Chameleon SDS, Amartus dynamic programmable service management and orchestration platform, and will describe how it addresses the problem. And Maurizio will then talk about how we are working with Intel and other partners to provide the solutions to orchestrate combined traditional and emerging network and cloud services. Service providers are facing an ever-increasing demand for high-quality, elastic, pay-per-use cloud and wide area network services. But most of the network service providers are currently providing static fixed-price network services. Some applications claim to be able to offer carrier-grade, reliable, scalable services to meet this requirement, but they do not solve the issue of long delivery cycles, which prolong time to market and negatively impact service providers' return on investment. The new virtualization technologies, NFV, SDN, cloud computing, provide a flexible infrastructure needed for on-demand service provisioning, but the existing static OSSs are too slow and cumbersome to support them. So software-defined service orchestration, or SDS, will enable service providers to provide dynamic network services over today's networks. So what is software-defined services, or SDS? It is a top-down, service-centric approach that provides the full service delivery lifecycle automation by abstracting the network with its different technologies, topologies, vendors, device types, applications. SDS then enables operators, end users, third-party apps to design, provision, and operate network services via Open API. On the other hand, network virtualization is enabled by SDN, NFV, and cloud, but it is bottom-up network-centric approach that still must be delivered in conjunction with SDS in order to provide a solution for long service delivery cycles. The solution being automated, dynamic, programmable, service design, provisioning, and operation. So here we have network services evolution and approach, but the same SDS capabilities are applicable to cloud-based services and higher value service offerings that combine software applications, compute, storage, and network. So what does the post-SDS era bring and what problems it solves? Current service design has no standard mechanism to introduce a new service. Services are hard-coded in software systems. We have multiple applications and APIs that need to be customized and integrated. Effects of that are long service rollout periods, sometimes months and years, and high costs. SDS, on the other hand, enables standardized mechanism to introduce any new service, dynamic introduction of services with zero coding, and single service-centric orchestration platform. Results of SDS-enabled service design then are designed within days to be first to market and significant cost reduction. Current service provisioning is part automated, sometimes mostly manual. We have long activation cycles, longer than 30 days, long service change cycles, longer than 5 days. There is a lack of true service inventory. Effects of that are considerable man effort, long activation period, high cost. On the other hand, SDS enables in service provisioning, it enables fully automated service provisioning, on-demand activation or change requests in minutes, comprehensive service inventory. Results of SDS-enabled service provisioning are automated procedures, activation within minutes, low cost. Current service assurance or service operations are network-centric, not service-centric. We have multiple systems, therefore high skill sets are required. The operations and assurance is reactive rather than proactive, and we have long resolution times. Effects are high cost of operations and low customer satisfaction. SDS enables service-centric approach where we have unified automated service-centric assurance, therefore lower skills required. We have proactive monitoring and detection which correlates all the troubles, traps, faults and statistics for performance and usage to services, and we have rapid resolution time. Results of SDS-enabled service operations are low operations costs and increased customer satisfaction. Key challenge for network service providers who are looking to automate their service delivery processes in their current OSS are silo of offline systems that cannot provide real-time service management. It is a key inhibitor when it comes to offering what is needed, the dynamic on-demand network services. One of the reasons is that typical OSS consists of general purpose point solutions designed to support the broad range of services the provider may offer, for example, network services, broadband, wireless, mobile, etc. They need a significant amount of costly and time-consuming customization to support specific service domains. As a result of that, we end up with the lowest common denominator when it comes to management capabilities, and this falls way short of what is needed. So what is needed is the system transformation that would provide real-time OSS with SDS that sits between the resource layer and the high-level DOSSs, providing a standard-based, fully programmable service layer abstraction that works both across traditional and virtualized networks. More importantly, it supports the full service life cycle, design, provision, operate on a single unified platform, eliminating the need for multiple point OSS applications and costly integration. SDS orchestration tackles the OSS problems head-on: lack of service awareness, hard wiring of services, technologies, vendors, lack of APIs, high development and integration costs. But critical for the success of SDS is the true service and network layer abstraction that is independent of vendor, service, and technology specifics. I would like to introduce you to a Amartus product called Chameleon SDS. Chameleon SDS overcomes the problems that I mentioned in the previous slide and provides the required software-defined service orchestration solution by combining the following two core concepts that we are focusing on. Firstly, by enabling dynamic introduction of new services into your real-time OSS through configuration only, without the need for new software releases, without the need to restart even the restart application. And we call it dynamic programmable service management and orchestration. Secondly, by providing the full service lifecycle automation in a single unified programmable service and network orchestration platform. And both of these core points are further elaborated on the next two slides. SDS solution must enable dynamic introduction of new services. So what does dynamic programmable service management and orchestration really mean? This is a new software paradigm that enables that the new service types and offerings that include completely new network technologies, topologies, graphs, vendors, device types can be introduced and configured runtime via metadata. These new service types are then supported by the existing service design, service provisioning, service operations, metadata-driven engines. Only by having a common services and resources model and through modeling services in a generic way and describing different service types, technologies, topologies, and rules with generic concepts, we can achieve dynamic runtime support for new network services and technologies without any coding. These generic concepts are service catalog with its service definitions, templates, hierarchies, graphs, and metadata for all service characteristics, faults, and performance and usage stats and rules. Also, service inventory with its service instances, configurations, service topologies, service components, subs, all the service characteristics. And also service assurance data with all service status info, performance and usage statistics, as well as all service problems, service test results, diagnostic results, service SLA compliance info, everything correlated to the services, not to the resources, to the services. So what you get out of the box with this runtime programmable, plugin-based and model-driven solution is dynamically rendered model-driven web GUI if needed, or dynamically rendered model-driven API out of the box. Also, dynamically model-driven reusable management modules that are used for any new types of services, even the future services that you don't know anything about at the moment when you are releasing. Then dynamically configurable service and resource models. Databases are auto-generated, and we also have dynamic model-driven device and application integration that is also pluggable, runtime pluggable. The second point, the second core concept is the full service lifecycle automation in a single unified programmable service and network and orchestration platform. So what does that really mean? It means we must provide service design, provisioning, and operations in a single platform. Service design is supported via dynamic programmable service catalog, which allows design of new service types, definitions, hierarchies, and templates, and that can be done either via GUI, XML configurations, or via API. Service provisioning then is provided via generic metadata-driven service topology and inventory, and service state engine with transactions and rollback capabilities. And also it's provided either by using a GUI or through API. Service operations then is supported via generic metadata-driven discovery, service sync, service assurance engine that provides comprehensive discovery, sync, status monitoring, faults, performance, usage management, test, troubleshooting, and diagnostic capabilities. It also means that it provides a single orchestrator for network services and network. It also provides a single and true service and network abstraction to different role service designer, operator, but also end users, higher-level OSSs, and third-party apps, where they don't have to understand all the multi-vendor, multi-service, multi-technology aspects, so they don't have to be domain experts in order to be able to integrate with Service Orchestrator. It also provides a single API for cloud and network services for design, provisioning, and operation. So this SDS approach and also Chameleon SDS platform solve the problems that network service providers currently have, including new service rollout in days, on-demand and seamless integration. Now I want to show you how service management and orchestration can be configured to provide life cycle management for a completely new service type. It is done without any code changes or software releases, fully dynamically runtime, even without restarting the application. So let's say that we have a Chameleon SDS application that supports cloud compute services only. Imagine this slide with only light green boxes here at the middle layer without the dark blue or orange or purple or blue boxes. So it supports the full service lifecycle management of the cloud compute services, meaning cloud compute service design, cloud compute service provisioning, and cloud compute service operations. It means it is already configured and integrated for cloud compute services. So the service catalog of the deployed application before the steps that I will describe later contains cloud compute service definitions with cloud compute service hierarchies, cloud compute metadata, cloud compute business rules, workflow plugins. The service catalog also contains the cloud compute service template or service offering, and it also contains a service inventory of cloud compute service instances for different customers, either discovered or provisioned. It is already integrated with the cloud and data center via southbound API for cloud compute services and provides the northbound API for template design, provisioning, and operations of cloud compute services. But the deployed application doesn't know anything about the network services or VNS, nothing about the types, roles, hierarchies, attributes, rules, task traps, mediation, integrated devices, integrated applications, or anything else for traditional or virtualized networks. So this slide describes the generic steps needed to dynamically introduce any new service type into the application, and from then on support management of new service type offerings and templates, as well as provisioning and operations of services of the new type. And that's the process we call dynamic programmable service management and orchestration. The slide shows an example of designing and activating cloud and connect services. The slide is focused on two phases, service design and service provisioning. And the first steps of the service design, define service and define mediation, are done only when a new service type is introduced into the system. The service designer will design a new service type by creating and storing the new service definition. And the service definition for Cloud and Connect will contain all metadata for that service. Hierarchy, or sometimes called topology or graph, roles for different access points and components of the service, for example, CVNF, PVNF, transport channels, customer endpoints, etc. Metadata for all service attributes, what attributes are set in templates, what attributes are set in during the provisioning of the services, and all different required plugins, tools, and validators for Cloud and Connect. The service template design is done whenever a new service offering for a same or similar service type is added. So GUI and API are auto-rendered based on the Cloud and Connect service definition, and only globally set attributes can be set during the service template design. The service designer may then create multiple service templates for a single service definition with different values for attributes, rules, and restrictions. For example, we can have gold, silver, and bronze Cloud and Connect service template. And then operator performs service provisioning whenever a new service instance for a customer needs to be provisioned. And in this case now, GUI and API are both auto-rendered based on the selected Cloud and Connect service definition and service template. So then the user only needs to select the service template. The user needs to pick the access points or components that the template and definition specify have to be picked, and has to set the subset, as small as possible, of the attributes that are service instance specific and must be set by the operator and cannot be auto-selected from the resource pool, for example. All other attributes and rules are reused by the applications from the service definitions and templates or taken from the resource pool. The slide shows the design and provisioning phases, but adding service assurance plugin is also done through dynamic extensions for service problems and service quality management. So I will hand over now to Maurizio. Maurizio, please.
Thanks, Olga. I will now describe how the Chameleon SDS generic service orchestration platform is being used to customize and package solutions that will allow service providers to exploit NFV, SDN, and cloud technologies and combine them with traditional WAN services into end-to-end services for their customers. I will then talk about how we are working with Intel and other partners on proof of concepts that integrate all these new and existing technologies to tackle the ongoing network transformation. In this diagram, we show how software-defined services orchestration sits between the network layer and applications, OSS, BSS, and portals to provide standards-based, runtime programmable service management and orchestration that works across any service or technology. As Olga explained, there are 4 key ingredients for this. A model-driven service catalog where new service definitions and templates can be introduced and onboarded at runtime. A set of service, technology, and vendor-agnostic management functions that are driven by the service models. A model-driven mediation layer to integrate south, east, and west with external systems models and APIs. And finally, standards-based open APIs exposing the service MANO operations northbound to applications, OSS, BSS, and portals, enabling for automated full service lifecycle support. Chameleon SDS initial focus was on service management and orchestration of traditional WAN services, such as Mass Carrier Ethernet, E-Line, E-LAN, E3, E-Access, as well as IP MPLS services, such as MPLS VPN, TE tunnels, TP tunnels, and several other legacy network services. Given its model-driven and service and technology agnostic architecture, it is a natural evolution for Chameleon SDS platform to be extended to model, manage, and orchestrate new services that span across traditional networks and new emerging virtualized network technologies, such as SDN and NFV. As Olga shown in a previous slide, the process to support any new virtualized network service or technology is no different from the process required to support a traditional network service. The key thing here, on the lower side of this diagram, is for SDN controllers, VNF, and VNF managers to expose their model through open APIs. Once the new service types are designed and the corresponding service definitions and templates are onboarded at runtime in the service catalog, all is needed is the mediation for mapping these service models southbound to the APIs exposed by the new external systems and functions. Using the same approach, the platform can be used as end-to-end multi-service management and orchestrator across WAN, SDN, and SDN cloud. For cloud services on the left-hand side, including computing, storage, and network, the end-to-end service orchestrator integrates with existing cloud managers or virtual infrastructure managers, such as OpenStack, to manage and orchestrate the required virtualized services and resources as components of the overall end-to-end services or service chain. Basically, Chameleon SDS, as depicted in the center of this diagram, enables service providers to exploit network controllers, VNF managers, and cloud managers' APIs to provide a higher level end-to-end customer-facing services abstraction to higher layer or higher level applications, OSS, BSS, and portals. The cloud and network services could be made available by different network and cloud providers. At this level of abstraction, only a few characteristics related to service access points and service level agreements are typically exposed through the end-to-end services API, while all details of specific underlying service components and technologies are handled in a transparent way, which helps maximize service agility for operations teams. This slide shows the roles that an end-to-end service management and orchestrator, such as Chameleon SDS, would cover, and how they map to the NFV reference architectural framework. Firstly, it shall provide a dynamic service and NFV catalog, where new end-to-end service types, including service chains, can be rapidly designed and onboarded at runtime. The service definitions and templates shall be flexible enough to model all service components for different services and technologies. These include service characteristics and descriptors for virtual network functions and DNS forwarding graphs for NFV, connectivity services for traditional and software-defined networks, and computing, storage, and networking for cloud services. The second role, depicted here, concerns the ability to manage and orchestrate the full life cycle of the newly introduced end-to-end services in an automated fashion. This includes service provisioning and activation, or instantiation as per NFV terminology, service assurance, including monitoring, service and related faults, ensuring performance matches the SLAs and running test diagnostics. Service updates and upgrades, including scaling out or scaling in, as well as service termination and retirement. Finally, for NFV specifically, Chameleon SDS can also optionally act as VNF manager and manage the VNF lifecycle, working with both the virtual infrastructure manager and directly with the VNF. This is useful in cases where VNF vendors do not provide a VNF manager for their VNF. This diagram shows how we are applying the approach we have described to an evolving proof of concept that shows how management and orchestration can span across traditional and new network technologies and the cloud. In this solution, Chameleon SDS acts as an umbrella end-to-end service manager and orchestrator for each of the following technologies. For cloud and SDN in the data center, it integrates with OpenStack for orchestrating computing, storage, and network resources in data centers via RESTful JSON APIs, exposed by the OpenStack modules. These include Nova for computing, Glance and Cinder for storage, Neutron for network, etc. Any cloud manager, on the left-hand side here, can be integrated via their APIs. Similarly, the data center network controller is currently orchestrated via Neutron API, but a separate API can be mapped if required, for example, when controllers such as OpenDaylight provide a more comprehensive API. For NFV, it acts as orchestrator and optionally VNF manager to orchestrate and manage virtual network functions lifecycle, including onboarding via OpenStack. As an example, we have integrated Clearwater IMS, which is a set of VNFs providing several core modules of an IP multimedia subsystem. For one on the right-hand side, it can integrate with any one or carrier SDN controller via its network services API. This can be RESTful XML, JSON, netconf, etc. In the current POC, the solution integrates with a separate instance of Chameleon SDS, acting as one controller for a carrier Ethernet network. We are continuously working with partners and service providers to expand the solution capabilities to support new services functions, and technologies. One of these initiatives is with Intel, to explore the possibility to expose Intel's OpenStack contributions for NFV and SDN, such as the enhanced platform awareness and DPDK Open vSwitch, through policy configuration that can be configured at the end-to-end service layer. Chameleon SDS performs best on carrier-grade, best-of-breed physical and virtualized platforms, which benefit from the latest Intel microarchitecture enhancements and maximize their performance leveraging Intel hyperthreading and virtualization technologies. In a nutshell, to support today's network transformation from traditional static fixed-price network services to dynamic, elastic, pay-per-use services over virtualized environments, service management and orchestration solutions shall, firstly, be able to orchestrate end-to-end services across one NFV, SDN, and cloud. Secondly, they need to be programmable. Service providers must be able to add new services and technologies at runtime through configuration and make them available to business applications via standards-based open APIs. They can no longer rely on lengthy software release, testing, and integration cycles. And finally, they need to support full service lifecycle automation, design, provision, and operate. These are all required to deliver elastic assured services that meet their SLAs at all times. These capabilities enable service providers to exploit the benefits of NFV, SDN, and cloud technologies as they mature and successfully combine them with traditional WAN services. The goal is to optimize service velocity and agility across all these network and cloud technologies, which will ultimately allow providers to, firstly, increase their revenues by greatly reducing time to market for cutting-edge new end-to-end services. Secondly, being able to offer a much broader range of end-to-end services, as well as achieving high customer retention by providing on-demand, higher quality, and customer-tailored services. Finally, providers will be able to reduce their CapEx and OpEx with lower costs for system purchase, service integration and rollout, and service operations and maintenance. I would now like to thank the audience for attending this webinar and Corey and Intel for hosting it. Thank you very much.
All right, so we have a few questions if you're interested. Excuse me. Let's start with the first one that we have here. What meta information do the service definitions and service templates have?
Shall I take this one?
Sure.
Okay, yeah. Service definitions describe the service types with the following information. They say what are the roles of different entities in that new service type. For example, they say there would be service access points of this type, there would be service components of that type. It also describes all the attributes for those different roles needed to be provisioned on the network or in the data center. They also contain all metadata for those attributes in terms of the validators for every attribute, minimal, maximum value for that service type, allowed values, whether it's required attributes or optional attributes, what are the list of allowed types, for example, whether the attribute has to be set during the design of the service template or service offering, or whether the attribute has to be provisioned by the operator during service provisioning, or whether that attribute is from the resource pools that are configured in the application. So the service definitions really describe the type of the service. Another thing is the hierarchies for that service. So in the network world, we call them topologies. Now in NFV, they are graphs, but they could be called either hierarchies, topology of graphs. They describe the structure and associations of the service as it has to exist in the network in the future, with cardinalities and containment relationships, something like a UML diagram of the service and all of its components and such. And it also contains plugins for what traps are supported, correlation rules, and statistics of the different types of subs, etc. So that is the service definition. Service template, on the other hand, is the one that provides more specific information for the different type of service offerings. So, for example, service template would fill in all the information from the service definition with some values for specific service offerings. So if it is, let's say, a gold service that needs 300 meg of bandwidth, service template would have that value added to the service definition so that multiple service instances can reuse the service template information. Does that answer?
Yeah, that does, I think. Let's see. How did you integrate with OpenStack APIs for compute, storage, and networking services in the cloud?
Okay. Thanks, Corey. I will take that question. So essentially, we did two steps to integrate with OpenStack APIs. First, we modeled a cloud service as a component that includes compute, storage, and networking specifications to specify, what flavor the instance, the virtual machine instance would have, what kind of storage characteristics, and networking in terms of segmentation, IP subnets, and so on. And then once we had the models introduced at runtime through our XML service definitions and templates, we used the platform RESTful adapter that we already had in terms of protocol, and mediated these cloud service components to the OpenStack RESTful JSON APIs. So we leverage their API, the Nova API for compute, the Cinder for storage, the Neutron for networking, and then the job was done. Essentially, we were able to orchestrate the compute, storage, and networking through OpenStack through our orchestrator.
Okay. So speaking of orchestration, how does the service orchestration layer support handle network errors during the provisioning? Does it support rollbacks?
Okay, yeah. The service orchestration layer supports the full transactions and also the full rollbacks. We have a service state engine implemented where we have a service first design in the inventory before it is provisioned on the network. So the service would be created in the inventory only in the case that there are no validation errors or its feasibility check passes. So that's the first phase. And the next phase is the network provisioning. So what Chameleon SDS does is has a policy-based provisioning where it can roll back and bring the service in the case of any network error into the initial state, which means nothing will be provisioned on the network by doing the termination of the existing of the individual bits and pieces that have been provisioned or activated before the error occurred. Our state engine supports similar to TMS-based state engine where you have feasibility check, design, provision with activate, provision without activate, terminate, deactivate from the network, terminate, or retire completely from the inventory.
Okay. You brought up states here, so I'll move to this question. Elaborate further on Chameleon SDS service state engine. What states does that support?
Okay, I think I did mention that in the previous answer that it does support design, service design state, service provision state, activated, terminated, and then you can retire. So it is also based on the TMS service state engine.
Okay. So here's a very specific question about plugins. Does Chameleon SDS have a Neutron plugin available today? Does it also have a plugin into the REST NBI of Open Daylight? to provide orchestration of open daylight controlled networks?
Okay. Essentially, the first part is at the moment we're not planning to position Chameleon SDS as southbound to OpenStack, and only northbound for multi-service end-to-end service orchestration. So currently we don't have a plan to support provide a Neutron plugin in that sense. And what we do have is the ability to orchestrate a Neutron, the Neutron API. So any technology, including Open Daylight, which has a Neutron plugin, we can orchestrate. Also, we can orchestrate them directly by providing a mediation layer to leverage their APIs. So it is in our plan to extend our list of pre-integrated technologies by providing a direct integration southbound to Open Daylight MBI.
Okay, great. One last question here. How can NFV service and VNFs be presented using your service definitions and the service templates?
Okay. Essentially, the required descriptors for VNFs, for wording graphs, virtual links, infrastructure resources, etc., can be modeled using Chameleon SDS by creating tailored service definitions and specifications and hierarchies and topologies like Olga explained earlier. So we create this, we model the service as required for VNF or the network service and service chains that use VNF. And then we model we create service templates that are then used to configure different service offerings, different flavors for the VNF and service chain.
Okay. Well, that looks like that's all the questions we had today. Thank you both for coming on and giving this overview. For more information, you can check out networkbuilders.intel.com. And if you have any other comments or questions for us, you can find us at Intel IT Center on Twitter. Thanks again, Olga and Maurizio.
Thank you, Corey.
Thank you, Corey. And everybody else, of course.